What if I told you that 16 AI agents working in parallel just built a C compiler from scratch? Not a toy compiler, a real 100,000 line compiler that can build the Linux kernel. The cost, $20,000. The time, 2 weeks. The human supervision, almost none. This isn't science fiction. This is what just happened at Anthropic. Nicholas Carlini, a researcher on Anthropic's safeguards team, ran an experiment that might change how we think about AI and software engineering forever. Let me break down what he did, what he learned, and why this matters. First, let's understand what agent teams actually means. Most of us use AI assistants one at a time. You ask Claude a question, it answers. You ask for code, it writes code. One human, one AI, back and forth. But what if you could run 16 Claudes simultaneously, all working on the same project, without you watching? That's exactly what Carlini built. Here's how it works. Each Claude agent runs in its own Docker container, cloned from a shared Git repository. When an agent finishes a task, it pushes its changes, pulls changes from other agents, and immediately picks up the next task. No human in the loop. No waiting for approval. Just agents coding, testing, and committing 24/7. To prevent chaos, there's a simple lock system. Before working on a task, an agent writes a log file. If two agents try to claim the same task, Git's merge conflict forces the second agent to pick something else. It's elegant, it's simple, and it works. The challenge Carlini gave these agents was deliberately extreme: build a C compiler in Rust from scratch that can compile the Linux kernel. Why is this hard? The Linux kernel is millions of lines of C code written over 30 years by thousands of developers. It uses every obscure C feature imaginable. It targets multiple architectures, x86, ARM, RISC-V. Building a compiler that handles all of this is a multi-year project for a team of expert engineers. Carlini wanted to see if AI agents could do it in weeks. After nearly 2,000 Claude code sessions and about $20,000 in API costs, here's what the agent team produced. A 100,000-line Rust compiler with 0 external dependencies. It can build a Linux 6.9 on x86, ARM, and RISC-V. It compiles QEMU, FFmpeg, SQLite, PostgreSQL, and Redis. It passes 99% of the GCC torture test suite. And yes, it can compile and run Doom, the ultimate developer litmus test. The whole thing is open source. You can go read it right now on GitHub. But here's the thing. The compiler itself isn't the most interesting part. The real value is what Carlini learned about orchestrating AI agents. These lessons might be more important than the code. Lesson 1. Tests are everything. When you're not watching, how do you keep agents on track? Tests, extremely high-quality tests. Carlini spent enormous effort building a nearly perfect test harness. The insight here is profound. If you want autonomous agents, you need a way to define correct that doesn't require human judgment. Lesson 2. Design for AI, not humans. Most software is designed for human developers. Error messages assume a human will read them. But AI agents have different needs. Context window pollution is real. If your test harness prints thousands of lines of output, the AI gets confused. Carlini learned to print only a few lines, log details to files, and pre-compute summary statistics. Lesson 3. Parallelism requires structure. When you have hundreds of failing tests, parallelism is easy. Each agent picks a different test. But what about compiling the Linux kernel? That's one giant task. Every agent hits the same bug, fixes it, and overwrites each other's changes. The clever solution: use GCC as an oracle. Compile most of the kernel with GCC, only use Claude's compiler for a subset, binary search until you find the bug. This let 16 agents work in parallel on what seemed like an atomic task. Lesson 4. Specialization works. Not all agents need to do the same thing. Carlini assigned the different roles. One agent coalesced the duplicate code. Another optimized the performance. Another maintained the documentation. This mirrors how human teams work. And it turns out it works for AI teams too. So what does this mean for the future? First, the economics are striking. $20,000 sounds like a lot, but a team of compiler engineers working for months would cost far more. Even the most expensive human expertise is becoming comparable to AI compute costs. Second, this is Opus 4.6, not some future model. The capabilities exist today. Third, the bottleneck isn't AI intelligence. It's orchestration. How do you break problems into parallel tasks? How do you verify correctness without humans? These are software engineering problems, not AI research problems, and that means they're solvable. But there's a sobering side too. This project ran in a container, isolated on a well-defined problem with clear tests. Real software isn't like that. Real software has vague requirements, changing specs, and no ground truth. The agents also made mistakes. They occasionally broke existing functionality. One agent even accidentally killed itself by running pkill -9 bash. We're not at fully autonomous software engineering yet, but we might be closer than most people think. Nicholas Carlini showed us something remarkable. AI agents can already collaborate on complex, long-running projects with minimal human oversight. The key isn't the smarter AI, it's better harnesses, better tests, better orchestration. If you can define what correct looks like, if you can break problems into parallel tasks, if you can design systems for AI instead of humans, you might be able to build things that would take human teams months or years. And that changes everything. Follow Nanhara deep dive into AI every week.